Welcome to lecture number 31 on this NPTEL course on fluid mechanics, and the topic that we are discussing currently is pipe flows and losses. We saw in the last lecture that the losses in a pipe are characterized by what is called the friction factor. Okay. So, just to briefly remind you, topic is pipe flows and losses. Okay. So, when the flow is in the laminar regime in a pipe, okay, that is when the Reynolds number, which is defined as the density of the fluid times the average velocity of the fluid times the diameter of the pipe divided by the viscosity of the fluid, is less than around 2000, then the flow is laminar. Then we were able to solve for the velocity profile inside the pipe, and we showed that the velocity profile is actually parabolic. Okay. After having solved for the velocity profile, we found the relation between the pressure drop and the volumetric flow rate, and that was a very simple relation. Okay. But we also showed that we also mentioned that when the Reynolds number is greater than, so when the flow is laminar, there is an analytical relation that exists between the pressure drop and the volumetric flow rate. Okay. That is a very simple expression that we wrote down in the last couple of lectures. Okay. Now, when the flow is not laminar, okay, then we have to take recourse to experiments, that is when the Reynolds number is greater than 2000, the relation between delta P and Q no longer is that was derived by assuming the flow is laminar is no longer valid. Therefore, we have to now take recourse to experiments. Okay. Now, experimental data we showed in the last two lectures can be best characterized by non-dimensional parameters. So, the non-dimensional pressure drop is called the friction factor. Okay. So, the friction factor is nothing but a non-dimensional pressure drop, friction factor is denoted by the symbol F, is defined as delta P by half rho V bar squared L by D, and the friction factor thus defined is called the Darcy friction factor, because there is another friction factor called the fanning friction factor, which is off by a factor of 8, okay, compared to this, or off by a factor of 4 compared to this. So, we have to be a little careful in the definitions, but generally the friction factors are essentially non-dimensional pressure drops across the pipe of length L and diameter D. Okay. Just by doing dimensional analysis, so dimensional analysis of the problem of flow in a pipe showed that the friction factor is a function of the Reynolds number and the non-dimensional surface roughness of the pipe. Epsilon is the measure of the, it's a length scale that tells you how rough the pipe is. It's, for example, it could be the mean squared root mean squared deviations of the fluctuations on the pipe wall. Okay. So, this is for a fully developed flow in a pipe, because only for a fully developed flow we could scale out the dependence on the length of the pipe by saying that delta P by L is a constant at any fully developed region across the pipe. Okay. If there are entry and exit regions where you are interested in measuring the pressure drop and flow rates, okay, then you cannot use this relation. We have to take into account the explicit dependence on the length of the pipe. Okay. So, this is only for a fully developed flow. So, we also showed that for laminar flow region, in the laminar regime, that the friction factor is nothing but 16 divided by Re, while in the turbulent regime you have to use the friction factor chart. Okay. So, the friction factor chart is merely an experimental observation condensed in the form of a non-dimensional relation. So, you are plotting f versus Re for different values of epsilon by d. So, in the laminar regime, so this is in a sense in a logarithmic plot. So, it is log f versus log Re in a double logarithmic plot. So, in the laminar region, f versus Re will have in a double logarithmic plot a slope of -1 because f is inversely proportional to Reynolds number. In the turbulent region, it is not very clear. So, there will be lot of fluctuations initially and this is for different values of epsilon by d. In the laminar regime, there is no dependence on epsilon by d, experimentally observed dependence on epsilon by d, while in the turbulent regime it does depend on epsilon by d. Okay. So, this is an experimental observation of pressure drop versus flow rate, which is reframed or reformulated in a non-dimensional sense and plotted in terms of friction factor and Reynolds number. Now, once we know the friction factor, then we can estimate what are the head losses in a pipe. Okay. For that, we have to take a pipe, a straight pipe. Okay. So, gravities are acting perpendicular to the direction of flow. The flow is in this direction and you apply energy balance. Okay. Macroscopic integral energy balance. When we do that, we take the stations of the control volume 1 to be like this and 2 to be like this. When we do that, we found that P1 by rho g plus alpha 1 P1 squared by 2 g plus Z1 minus the same quantity evaluated at the exit P2 by rho g plus alpha 2 squared by 2 g plus Z2 is equal to the head losses in the pipe, because there is nothing else that is happening. There is no shaft work between the two ends of the control volume 1 and 2, and the only loss is due to the fact that the fluid is flowing and there is viscous dissipation of energy. So, for a steady fully developed flow, which is what we are going to assume, we are not going to assume the flow is laminar or turbulent. We are going to say that it is a steady fully developed flow. I have to make one remark regarding the meaning of steady for a turbulent flow, because it seems like a contradiction in terms, because a turbulent flow, as I told you, is inherently unsteady. The flow velocity depends at each and every point in time, with time in a very random way, in a chaotic way. Here what we mean by steady is that if you take a substantial time interval and then average the velocity, so that time average velocity remains independent of time. So, you can imagine having a pipe flow experiment. Let us say the flow is in the turbulent regime, because Reynolds number is greater than 2000. Then you can, let us say, measure the velocity at a given point in space for about 5 minutes and then take an average, and then you can measure the velocity at the same point after some time again for 5 minutes. So, that time average quantity will itself be independent of time. So, what we mean is that average quantities, time average quantities are steady. So, this is called steady in the mean. Although there are fluctuations about the mean flow, the mean itself is independent of time. So, that is what we mean by steady flow. So, when you have steady fully developed flow, mass conservation equation will mean that V1 is V2, because this is a pipe of straight cross section, and alpha 1 is alpha 2, because the conditions are identical in both the cases. It is either turbulent, it is not like it is turbulent in one end and laminar in the other end. So, these two terms will cancel each other out, and since the pipe is oriented horizontally, Z1 is also equal to Z2, leaving us with this simple expression, delta P by rho g is HL pipe, where delta P is nothing but P 1 minus P 2. This is our convention. The pressure at the entry minus the pressure at the exit is the pressure difference across the pipe. Now, so all we have from the energy balance is delta P by rho g is head loss in a pipe. Now, I want to relate it to the friction factor. If I want to relate it to the friction factor, I have to simply include the invoke the definition of friction factor. F is nothing but delta P divided by half rho v squared L by d. Okay. If that is the case, then I have to take this equation. Okay. I have to take this equation. Now, all I have to do is divide both sides by half v squared g L by d, because then I will get half v squared L by d, because g is already just half v squared L by d, okay, and multiplied by g, so that I get friction factor. Okay. So, if I do that, I will get delta P, okay, by half rho v squared, okay, L by d, because I am multiplying by g, is equal to H L pipe times g. Okay. So, I am sorry. So, I have to divide by g or multiply this entire equation, let us call it multiply by g divided by half v squared L by d. So, that I get friction factor on the left side of this equation. On the right side, I will get H L pipe divided by half v squared L by d. Since this is the friction factor, the Darcy friction factor F, I can write, therefore, H L is nothing but F times half head loss in a pipe, half v squared L by d, okay, divided by g. Okay. So, this is the relation between the friction factor and the head loss in a pipe. Okay. This is the relation between the friction factor and head loss in a pipe. Okay. Why is this important? This relation important, because when we want to write the energy equation for a complex flow setting, for example, in practice you may have a problem like this. You may have a reservoir in which there is a liquid, and you want to have a pipe, and you want to maybe pump the fluid at a given flow rate, and there may be valves to some other elevation. So, this is a typical problem. This is elevation Z1, let us say this is 0.1, and fluid is coming out to the atmosphere, and this is, let us say, 0.2. Okay. If you want to write the energy balance between points 1 and 0.2, okay, the general energy balance, of course, we know is P 1 by rho g plus alpha 1 V 1 squared by 2 g plus Z 1 minus P 2 by rho g plus alpha 2 V 2 squared by 2 g plus Z 2 is equal to head losses in the flow minus any work done by the pump on the fluid. So, there is a pump here, which inputs energy constantly to the system. Okay. So, this is a typical setting that one would like to solve. For example, we may want to ask the question, suppose I want, this is a static fluid, stationary fluid. Okay. So, flow is, there is no flow here, and this is atmospheric pressure, and fluid is exiting to atmospheric pressure at 0.2. Then the question you may ask is, suppose I want the fluid to come up with a specific velocity V 2, this is given to us. Okay. Now, what is the head loss, what is the head I must generate across the pump, so that we can make the fluid flow at a particular velocity. What this pump is essentially doing is to overcome the gravitational head between points 1 and 2 and also the viscous losses that occur at various points. Now, there are various segments in which the flow is straight. There is a flow, the flow is through a straight pipe. Here we have to estimate the losses using the friction factor chart. So, whenever there are segments of pipes where there are straight segments, then those pieces will, the losses in those pieces of the pipeline network will have to be calculated from friction factor chart. Such losses are called traditionally major losses. Major losses, because they contribute numerically the most to the losses present. So, major losses are losses through straight segments of pipes. They must be calculated from friction factor charts, must be inferred from FRE charts. But that is not to say that this is the only source of losses for the flow system, because there are also other pieces such as the flow is static here, but it is entering a pipe. So, these are called entry losses, and there is a bend of various types throughout the pipeline. These bends will in general have losses. There are valves here which will have losses depending on the nature of the valve. So, and there is a exit, the fluid is exiting from the pipe to the atmosphere. So, there are losses associated with exit. So, viscous losses are not just there when you have straight sections of pipe, as we also saw while doing the integral momentum balance. Whenever you have a sudden expansion or contraction of flow cross section, then there are recirculating eddies in the immediate vicinity of the expansion or contraction, which will contribute to additional losses. So, we incur additional losses due to various reasons. Those are called minor losses for the simple reason that they do not numerically contribute much to the losses. They contribute maybe 10% to the total loss, but they are the minor losses typically include bends, entry, exit, valves, sudden expansion, contraction, and so on. So, there are various reasons why there could be minor losses in a problem. So, these minor losses have to be calculated by correlations. So, let us again rewrite, let us split this losses into major losses, which I will denote as HL pipe, and minor losses, which I will just write as HL minor. It depends on the nature of the problem and nature of the type of losses that occur in a given flow system. So, the major losses will have to be calculated from friction factor charts. The minor losses will have to be again derived from experiments, but they have to be there are standard values that are written down for minor losses. Typically, the minor losses are written as or correlated as a loss coefficient times V squared by 2G. This is called a loss coefficient. So, this coefficient will be different for different types of losses. For example, for entry this may be 0.8, for a sudden for a valve, for a globe valve, a partially closed valve or a fully open valve, it will have different values and so on. So, these are typically given in textbooks and handbooks. So, these are not these are merely experimental facts, because the actual flow that happens in these bends and through valves is extremely complex for us to be able to calculate these losses exactly using any fundamental means. So, we have to take recourse to experiments, and in experiments we characterize these losses as the minor loss head as a loss coefficient, which is a non-dimensional number, and that number varies for varying types of various losses. So, the total loss will therefore be, the total losses in the pipe will be V squared by 2G times F times L by D plus summation over various minor losses, okay, V squared by 2 G times the loss coefficients. Okay. Varying, there could be varying losses. So, over sum over all losses. Okay. So, this is the typical way in which losses are computed. Okay. So, when you want to compute the losses, there is a small detail that one has to understand properly. Okay. Suppose we are interested in computing the major loss. So, HL pipe is nothing but half F L by D V squared by G. Okay. Now, when can we calculate HL by D, HL pipe? Okay. So, there are three types of questions that can occur. In class 1 questions, we are given the volumetric flow rate, the pipe diameter, the length, the density of course and viscosity, nature of the fluid. So, this is essentially volumetric flow rate and diameter essentially means we are given the average velocity. This means that we can calculate the Reynolds number. Okay. So, once we know the Reynolds number, we can use friction factor charts to find the friction factor. Once you know the friction factor, you can find the major loss through this expression. So, this is a very linear progression, that is, we are given, suppose somebody asks the question, given the fact that we have a flow rate, how much what is the loss that is incurred in a pipe of given diameter and fluid is known. So, we can readily do this calculation by knowing the flow rate and the diameter of the pipe. We can calculate the average velocity. By knowing the average velocity, we can calculate the Reynolds number, then use the friction factor chart to look up for what is the friction factor corresponding to the Reynolds number, then use this equation, okay, for calculating the losses. Okay. That is class 1 problem. Now, there can be other class of problems also. Okay. Suppose you know what is delta P, then diameter L, rho, mu, and we are asked to find the velocity or volumetric flow rate. Now, with this set of variables, RE cannot be calculated. Because we do not know what is the velocity, that is the final goal of our calculation. So, these kind of problems must be done iteratively. That is, guess a velocity, then calculate RE, then calculate F, then calculate head loss. Okay. Now, once if you look at the head loss expression, okay, the head loss itself is given by the definition of head loss is nothing but delta P by rho G. Okay. So, given delta P, we can calculate what is the head loss. Okay. The definition of head loss is delta P by rho G, okay, for a straight section of a pipe. Okay. If you notice this part, this is delta P by rho G is the head loss in a straight section of a pipe. Okay. So, and we are now restricting ourselves to only straight sections. We can add on minor losses a little later. Okay. So, you obtain a head loss, compare with the given head loss, that is, once you know delta P, you can actually calculate the head loss. If they do not agree, then keep doing it. If do not agree, again refine your guess for V, do this thing. If agrees, then you have answer as converged. So, if you are given the delta P, that is the pressure drop across a pipe, and if you are asked to calculate the velocity, it is not a straightforward calculation, because if you are given delta P, all we are given is the head loss, and if you want to calculate head loss, the average velocity from the head loss, then first you have to guess a velocity, then calculate the Reynolds number, because the pipe diameter is given and the fluid nature of the fluid is given to us, properties are given, calculate friction factor, and then use the relation between friction factor and head loss, see whether this head loss, calculated head loss, agrees with the given head loss. If not, keep refining and do this iteration until you converge for a suitably satisfactory answer. Okay. And the third type of problems is given delta p, okay, delta p, length, velocity, rho and mu, and you are asked to find the diameter. Suppose in an application you are saying that, well, my pressure drop across the two ends is fixed and I want to pump the fluid with a given flow rate and the length of the pipe is fixed, but all I want to do is know what is the diameter that I have to choose, okay, because in many cases you may be forced to work with a given length, okay, and your pumping requirements are such that maybe delta p is also fixed and you want a particular velocity. So, v is fixed. So, the only variable in your hand is actually the diameter of the pipe. Again, the answer is not a straightforward answer, you have to do it iteratively. Guess d, then everything else is known, calculate Reynolds number, calculate friction factor, calculate head loss. Now, head loss is also given because delta p is given, compare with given head loss, with head loss that is given, okay. Then if not agree, if it does not agree, okay, this again you refine your value of d. If it agrees, then you have a converged answer. Okay. So, these are the three kinds of questions or types of problems that one can often encounter in pipe flows, especially if you have straight sections of pipe. Then it really, you cannot use straightforward solution if you are asked to find, for example, the velocity for a given pressure drop or diameter for a given pressure drop, because those solutions are iterative. The primary reason being that the F versus RE chart is a nonlinear relation in the turbulent regime. Therefore, you have to use iteration to find the solution, okay. And the data is known only graphically, it is not available as a simple relation. So, you have to do iteration, okay, in a graph sheet. You have to do a graphical iteration to find the solution, okay. Now, let us go to the case of pumps. Okay. So, essentially let us say you have a system where you have, again let us go back to the same example, you have a free surface and then you have a pump and then you have valves and then you are writing the balance between point 1 and 2. Typically the questions that will happen that will arise in engineering is that, suppose I want to pump the fluid with a given flow rate from station 1 to station 2, what must be the rating of the pump? That is, what is the horsepower rating of the pump, in which in a sense means what is the rate at which the work must be done by the pump on the CV, so that you can get the required flow rate, which will be essentially the horsepower rating of the pump if the pump is 100% efficient. In principle, there may be some mechanical inefficiencies in a pump. So, you will have to account for that a little bit, that is an experimental fact, but theoretically speaking, what is the rating of a pump for a given application? In order to do this, we have to just write the energy balance across the inlets and exits of a pump. Okay. So, the rate at which pump does work, W dot pump, is m dot times P1 by rho plus V1 squared by 2 plus GZ1 minus P2 by rho plus V2 squared by 2 plus GZ2. This is the mass flow rate. Okay. Now, and this is the rate at which work is done by the pump is done by the pump on the fluid. Okay. So, this is the rate at which work is done by the pump on the fluid, and so let us simplify this balance. Okay. So, P1 minus P2 is not negligible, because that is the whole point of having a pump. You want to increase the pressure head across the pump, and if the pipes that connect the inlet and outlet of the pump are of the same dimensions, okay, then you can neglect V1 squared and V2 squared is approximately same. Okay. And the elevation difference between points 1 and 2 is also typically negligible. So, W dot pump is nothing but the rate at which work is done by the pump on the fluid is nothing but m dot times delta P, P1 minus P2 divided by rho. Okay. Now, m dot is mass per unit volume, rho m dot is mass per unit time, rho is mass per unit volume. So, m dot by rho will essentially give you q dot times delta P. This is the volumetric flow rate of the pump times the pressure difference across the pump will give you the rate at which work is done by the pump. Work must be done by the pump in order for the fluid to generate a pressure difference of delta P. Now, so W dot pump, to go back, is nothing but, so if we have this notation of heads, which is nothing but W dot pump divided by m dot times G. So, this is nothing but delta P pump by rho G. Okay. So, this H pump is nothing but delta P pump by rho G, where delta P pump is the pressure difference P1 minus P2 across the pump. Okay. So, P. Okay. Now, sorry, this one, sorry, this is at station 2 minus station 1, I made a mistake. So, this is minus of W pump. Okay. So, this is P2 minus P1, because P2 is greater than P1 in a pump, the pressure at the exit is greater than. So, delta P in a pump is defined as, let us, instead of calling it P2 minus P1, let us call it P discharge minus P inlet, and this is delta P. It is a positive quantity, the discharge pressure is greater than the inlet pressure. Okay. So, so H pump, which is what we require in our calculations, is nothing but delta P pump by rho G. Okay. So, suppose you have this typical problem in which you have a reservoir and its atmospheric pressure here, and you have a pump that has to pump it through a series of bends and say various valves to finally again to atmosphere with another velocity V2. So, let us call this station 1 and this station 2. Suppose we are given and the stations are at Z different elevations, Z1 and Z2. The two stations are at different elevations. So, if you write the energy balance between point 1 and 2, okay, all you will get is P1 by rho G plus alpha 1 V1 squared by 2 G plus alpha plus Z1 minus P2 by rho G plus alpha 2 V2 squared by 2 G plus Z2 is equal to the total losses, which is the major loss due to pipe plus the minor loss due to bends and valves and so on, minus H pump, where this is the head, this is the in some sense the work done by the pump on the fluid. Okay. So, that is why it is coming with a negative sign. Remember that if you have if you have work done by the fluid on the surroundings, then this would have come with a positive sign. Since in our case we have used the convention that work done on the system is negative, this comes with a negative sign. Okay. So, if you have this kind of a problem, so we have P1 is P2 is atmosphere. So, we neglect this. Now, V1 is stationary, fluid is stationary there, static. So, V1 is approximately 0, but you have Z1 minus Z2 which is non-zero, and V2 is non-zero. We know what the value of V2 is. Okay. Using what is V2, the velocity in the pipes, we can calculate the major loss as well as the minor loss, from which you can find H pump. H pump is nothing but delta P by rho g. Okay. Now, once you know what is delta P, okay, once you know H pump, you can find delta P. Once you know delta P, then the rate at which work must be done by the pump on the fluid is nothing but Q dot times delta P. This is delta P across the pump. Okay. And if you take this delta P, you can find the horsepower rating of the pump. This is the power requirement of the pump, provided the pump is 100% efficient. Of course, if there are mechanical inefficiencies, then one has to correct them by increasing the actual power rating of the pump, because in principle the pump will be characterized by a mechanical efficiency. So, the rate at there is a conversion factor from the electrical power that is supplied and the mechanical power that is gotten as an output from the pump. So, this will be the ideal horsepower rating of a pump, ideal power rating of a pump. Okay. So, this is a very important application of the notion of losses in a pipe, major losses and minor losses in a pipeline network. Typically, they are used to calculate quantities such as what is the rating of a pump, or alternatively, suppose you have installed a pump of a given rating, then you know what is H pump, then you can ask the question what is the velocity. In such a case, the answer is not straightforward, because we have to find out the velocity through an iterative procedure, because we do not know what the Reynolds number is in order to find what are the losses. So, both kinds of problems are equally possible in practical engineering applications in chemical process industries. That is, if you want to design a pipeline network, okay, no matter how complex it is, the ideas are essentially what we have been discussing. Okay. Typically, you may have a pump, and then you may want to find what is the velocity in a pipe, and that is a iterative problem. But if you are asked to design a pump, that is, if you want a given flow rate, okay, and then if you are asked to design a pump, that is what is the horsepower rating of the pump, then you have to follow the procedure that we just outlined. Okay. This essentially completes my discussion on pipe flows and losses, and the topic that we are going to discuss next is fluid flows at high Reynolds numbers. In many industrial applications, okay, when you calculate the Reynolds number at which fluid flow is occurring, they typically happen at very high Reynolds numbers. And Reynolds numbers, by high I mean Reynolds numbers of the order of 1000 and higher, maybe 5000, 10,000, things like that. So, it is good to have some fundamental understanding of what is happening at high Reynolds number flows. Okay. Now, the problem with, as I have told you, the problem with Navier-Stokes equations, the Navier-Stokes equations are written down about 200 or 300 years back really, but they are extremely complex to solve. The Navier-Stokes equations for an incompressible fluid, okay, they are non-linear and partial differential equations. So, let us write that. Okay. So, it is extremely difficult to solve the Navier-Stokes equations in a general setting without making suitable assumptions, because they are extremely complex to solve. Okay. So, often to gain some insight into a problem, it is useful to simplify the Navier-Stokes equations by neglecting some terms which are at the outset somewhat small compared to other important terms. The Navier-Stokes equations is essentially a force balance equation. So, there are various forces on the various sides of Navier-Stokes equations. The left side you have the inertial forces, and on the right side you have the pressure forces, the viscous forces and the gravitational body forces. Okay. So, these are the various forces that act on a fluid element. Okay. By looking at particular flow regimes, for example, when the Reynolds number is very small, we know from interpretation of Reynolds number that the Reynolds number is a ratio of inertial forces in the system to viscous forces in the system. When the Reynolds number is very small, we can presumably neglect inertial forces to begin with and hope to get a reasonable approximation to the actual flow by just worrying about the balance of viscous forces, pressure forces and body forces. Likewise, when the Reynolds number is very high, very large, that is of the order of thousands, okay, then we can hope that since the Reynolds number is very large, we can hope that the inertial forces in the fluid must be dominant compared to viscous forces in the fluid, and therefore, we must be able to get a suitable approximation by neglecting viscous forces altogether. So, it seems like a reasonable proposition, and that is what we will do to begin with. Also, this approximation, which seems like a very reasonable one to make to begin with, has some serious difficulties, and we will point that out a little later when we come to boundary layer theory. Okay, and we will keep pointing out the deficiencies of the approximation as we go along, but right now we are going to write down the non-dimensional version of Navier-Stokes equation. It is nothing but Re times del V del T. These are all starred variables because they are all non-dimensional, plus is nothing but minus del star P star plus 1 over Re. I am going to neglect body forces for the moment because they do not play an important role right now. So, we can say if there are no body forces, then this is the I am sorry, I have taken Reynolds number to this side. So, when Reynolds number is very large compared to 1, that is, it could be of the order of thousands, then 1 over Re is small. So, the viscous forces, the non-dimensional viscous forces that occur in the Navier-Stokes equation are multiplied by a small number. So, we can hope that we can neglect viscous forces altogether to begin with. Okay. And if we neglect viscous stresses, then we end up with what is called the Euler equation. So, the non-dimensional Euler equation is simply partial V star partial T star plus this minus del star P star. Okay. And if there is gravity, we can write gravity, but if there is none, we can just leave it like that. So, this is the non-dimensional Euler equation, but we will get the dimensional, we want to work with the dimensional Euler equation to begin with. So, we will write down the dimensional Euler equation, which is nothing but rho V is minus del P, and if you have body forces plus rho G. Okay, this is rho. Now, I want to further simplify this equation or rewrite this equation, for which, and then of course, we have the continuity equation or the mass conservation equation for an incompressible fluid, which is the divergence of velocity vector is 0. We will use a vector identity to rewrite this equation. So, there is a standard vector identity that V dot gradient of V can be written as del of half V dot V plus del cross V cross V. Now, del cross V is the curl of the velocity vector, it is called the vorticity vector in fluid mechanics. It is the curl of velocity. Velocity is a vector. If you take the curl of velocity, you will again get a vector, that is called the vorticity vector. So, this is essentially what nothing but omega cross V. Okay. So, I am going to write the Euler equation, rewrite the Euler equation as follows, okay, plus del of half V dot V plus vorticity cross V plus 1 by rho grad P minus G. Okay. Now, I am dividing the entire equation by rho, so that I get rho here. Okay. Okay. So, I am dividing this entire equation by rho, I am dividing by rho to get just a rho and del P by rho, and this rho will cancel out, minus G is 0. This is the Euler equation rewritten using the vector identity. Now, I am going to take the Euler equation, the above equation, and dot it with a small vector, displacement vector dr along the fluid. It is an arbitrary displacement vector between any two, it is an infinitesimal vector, arbitrary infinitesimal displacement vector between any 2 points in the fluid. Okay. It is a vector. Now, in order to simplify, okay, so we will write this above equation therefore, as this entire equation dotted with dr is 0. So, I am taking the entire equation and dotting it with 0. In order to simplify this equation, I should somehow get this term omega cross V dot del r to 0. Okay, let us discuss the circumstances. When is omega cross V dot del r is 0? The first thing you will say is, well, when V is 0 and there is no flow, that is a trivial case. So, we will not discuss this. Secondly, when omega is 0, such flows when the curl of velocity is 0, they are called irrotational flows, because omega, it turns out, tells you how much circulation is there in a velocity field, in a flow field, that is how much there is fluid rotation that is there about a given point. Okay. It does not tell you about the rigid rotation of the entire body of fluid, but it tells you if omega is non-zero, that means that about a given point in fluid, if omega is non-zero, that means about a given point in fluid, the neighboring points undergo a rotation motion. Okay. If omega is 0, no such thing exists. That is how such flows are called irrotational flows. Okay. So, that can happen, and omega cross V dot dr can be 0 if V is parallel to dr. That is because if V and dr are parallel, then omega cross V will point in a direction perpendicular to V, because the cross product of two vectors points in a plane perpendicular to the vectors. If V and dr are in the same direction, then omega cross V will be orthogonal to dr. So, the dot product of the two vectors is 0. When V is parallel to dr, what we get is a streamline, because if you take any 2 points dr, okay, the definition of stream function is such that V cross dr is 0, that is V is parallel to dr and V cross dr is 0. Okay. So, this can also happen, that for along a streamline omega cross V dot dr is again 0, and finally, there is a very obscure or very rare case, that is dr is perpendicular to V and omega, because then V cross omega dot dr will be 0, because if dr is perpendicular to V cross sorry, not V and omega, it is V cross omega. Sorry. Dr is perpendicular to V cross omega, obviously this term is 0, but that is a rare case, okay, of it is not important. Okay. So, what we are interested in are in two cases, that is omega itself is 0 that is irrotational flows, which is much more stronger. And then another case where omega cross v dot dr is 0, not because omega is 0, but because v is parallel to dr, that is a streamline. Okay. So, we will consider this case, consider along a streamline, consider dr along a streamline. Okay. So, that you get this immediately says that omega cross v dot dr is 0, and the Euler equation for such a case becomes del v by del t dot dr plus d. So, you have gradient of half v dot dr, okay. Then you have plus del p dot dr plus g del p by rho dot plus g. Now, let us take the acceleration due to gravity vector in the direction of minus z. So, it is, let us write this g k, okay, times the unit vector in the k direction. So, you have the acceleration due to gravity. So, you have, let us see, you have minus g vector, I am sorry, this is a vector, okay. This is a vector here, sorry for that. So, you have minus g k dot dr is 0. Okay. Now, that is the relation. Now, let us try to simplify this further. Now, gradient of any scalar quantity dotted with dr will give you the differential change in that quantity along the two endpoints of the vector. Okay. So, this equation therefore becomes partial v partial t dot dr plus the change in half v dot v plus the change in the pressure across the 2 points minus k dot dr is nothing but the difference in, suppose you have a unit vector, sorry, you have a differential vector in some direction, this is the projection of that vector along the k direction. So, this will merely tell you what is z2 minus z1. Suppose you are, so let us just write it as minus g dz. So, k dot dr is dz, because dr is dx times I plus dy times j plus dz times k. Okay. Now, so this is equal to 0. Now, I am going to integrate between any 2 points. This is a differential relation that is valid only for a very small displacement dr vector, but if I integrate between any 2 points along a streamline, which I am free to do between any 2 points along a streamline, I get integral 1 to 2 partial v partial t. Okay. This is the arc length along streamline. So, you will get, so it becomes a scalar plus integral dp by rho plus half v 2 squared minus v 1 squared plus g times z. So, I am sorry, there is a, since g is in the plus k direction, g is actually in the minus k, there is already a minus g here. So, it will become a plus g. Okay. So, there is a plus g here, plus g times z2 minus z1 is 0. There is a minus g because if you look at the original equation, it happens with a minus g, and since g was aligned in the minus k direction, the two minuses will cancel to give a plus sign. It is equal to 0. Okay. Now, let us consider an incompressible and steady flow. Steady flow, then we will have, so in steady means this is 0. So, you will have P 1 P 2 minus P 1 by rho, rho is constant. So, you can integrate this. So, it becomes integral of dP, which is P 2 minus P 1 by rho plus half V 2 squared minus V 1 squared plus G Z 2 minus Z 1 is 0, or I can rewrite this as P 2 by rho plus half V 2 squared plus G Z 2 minus P 1 by rho plus half V 1 squared plus G Z 1 is 0. Since points 1 and 2 are arbitrary, all this means is that P by rho plus half V squared plus G Z is a constant along a streamline. And this is the famous Bernoulli equation, which we derived it as a consequence of integral energy balance, but we had to make assumptions that the control volume is essentially a stream tube, and we shrunk the stream tube to the limit of a streamline and assumed that there is no viscous shear stresses by the surrounding fluids. Of course, that assumption is there here also, that we are assuming the fluid to be an inviscid fluid, but once you assume the fluid as inviscid fluid, the Bernoulli equation directly comes out as a consequence of the momentum balance, the Euler equation, and by manipulating the momentum balance, we were able to derive the Bernoulli equation, which says that P by rho plus half V squared plus Gz is a constant along a streamline. Okay. So, that is the Bernoulli equation. Now, we can also say what will happen if omega is 0. That was along a streamline. If omega itself was identically 0, then it means that P by rho plus half V squared plus Gz is a constant not just along a streamline, but along any 2 points in the fluid. So, these are two different assumptions. In the first case, we are not saying omega is 0, we are merely saying that the flow is inviscid, that is the viscosity is 0. Then the Bernoulli equation is valid only along a streamline, along any 2 points along a streamline. But if you are saying that the flow is irrotational, then the Bernoulli equation is valid along any 2 points across the fluid, even across streamlines. So, these are two different types of assumptions that are used, and one has to be careful in interpreting the two assumptions. We will stop here at this point, and we will continue with this theme in the next lecture also. Thank you.